The center selection problem. Like the problem in the previous section, the center selection problem, which we consider here, also relates to the general task of allocating work across multiple servers. The issue at the heart of center selection is where best to place the servers. In order to keep the formulation clean and simple, we will not incorporate the notion of load balancing into the problem. The center selection problem also provides an example of a case in which the most natural greedy algorithm can result in an arbitrarily bad solution, but a slightly different greedy method is guaranteed to always result in a near optimal solution. The problem: consider the following scenario. We have a set S of n sites, say n little towns in upstate New York. We want to select K centers for building large shopping malls. We expect that people in each of these n towns will shop at one of the malls, and so we want to select the cities of the K malls to be central. Let us start by defining the input to our problem more formally. We are given an integer k, a set S of n sites corresponding to the towns, and a distance function. When we consider instances where the sites are points in the plane, the distance function will be the standard Euclidean distance between points, and any point in the plane is an option for placing a center. The algorithm we developed, however, can be applied to more general notions of distance. In applications, distance sometimes means straight line distance, but can also mean the travel time from point S to point Z, or the driving distance, i.e., distance along roads, or even the cost of traveling. We will allow any distance function that satisfies the following natural properties. Dist of SS is equal to 0 for all little s in S. The distance is symmetric. Dist of sz is equal to dist of zs for all sites s and z in capital S. The triangle inequality. Dist of sz plus dist of zh is greater than or equal to dist of sh. The first and third of these properties tend to be satisfied by essentially all natural notions of distance. Although there are applications with asymmetric distances, most cases of interest also satisfy the second property. Our greedy algorithm will apply to any distance function that satisfies these three properties, and it will depend on all three. Next, we have to clarify what we mean by the goal of wanting the centers to be central. Let C be a set of centers. We assume that the people in a given town will shop at the closest mall. This suggests we define the distance of site S to the centers as dist of SC equals to the minima of dist of SC, where the minima is taken among all possible little c in capital C, that is a little center of the set of centers. We say that C, the capital C, forms an R cover if each side is within distance at most r from one of the centers. That is, if dist of SC is less than or equals to r for all sides little s in capital S, the minima little r for which capital C is an R cover will be called the covering radius of C and will be denoted by R of C. In other words, the covering radius of a set of centers C is the farthest that anyone needs to travel to get to his or her nearest center. Our goal will be to select a set C of K centers for which R of C is as small as possible. Designing and analyzing the algorithm. Difficulties with a simple greedy algorithm. We now discuss greedy algorithms for this problem. As before, the meaning of a greedy here is necessarily a little fuzzy. Essentially, we consider algorithms that select sites one by one in a meiotic fashion, that is, choosing each without explicitly considering where the remaining sites will go. Probably the simplest greedy algorithm would work as follows. It would put the first center at the best possible location for a single center, then keep adding centers so as to reduce the covering radius each time by as much as possible. It turns out that this approach is a bit too simplistic to be effective. There are cases where it can lead to very bad solutions. To see that this simple greedy approach can be really bad, consider an example with only two sides, s and z, and k equals to 2. Assume that s and z are located in the plane with a distance equal to the standard Euclidean distance in the plane, and that any point in the plane is an option for placing a center. Let d be the distance between s and z, then the best location for a single center c1 is halfway between s and z, and the covering radius of this one center is r of the singleton c1, which is equals to d over 2. The greedy algorithm would start with c1 as the first center. No matter where we add a second center, at least one of s or z will have the center c1 as closest, and so the covering radius of the set of two centers will still be d over 2. Note that the optimal solution with k equals to 2 is to select s and z themselves as the centers. This will lead to a covering radius of 0. A more complex example illustrating the same problem can be obtained by having two dense clusters of sites, one around S and one around Z. Here, our proposed greedy algorithm would start by opening a center halfway between the clusters, while the optimal solution would open a separate center for each cluster. Knowing the optimal radius helps. In searching for an improved algorithm, we begin with a useful thought experiment. Suppose for a minute that someone told us what the optimal radius r is. Would this information help? That is, suppose we know that there is a set of k centers, c star with radius r of c star, which is less than equals to r, and our job is to find some set of k centers c whose covering radius is not much more than r. It turns out that finding a set of k centers with covering radius at most 2r can be done relatively easy. Here is the idea. We can use the existence of the solution c star in our algorithm even though we do not know what c star is. Consider any site little s in capital S. There must be a center little c star, which is in capital C star, that covers site S, and this center c star is at distance at most r from S. Now, our idea would be to take this site S as a center in our solution instead of C star, as we have no idea where C star is. We would like to make S cover all the sites that C star covers in the unknown solution C star, capital C star. This is accomplished by expanding the radius from r to 2r. All the sites that were at distance at most r from center C star are at distance at most 2r from S by the triangle inequality. See figure 11.4 for a simple illustration of this argument. So the algorithm is as follows. S prime will represent the sites that still need to be covered. Initialize S prime equals to S, and we let C equals to the empty set, the set of centers that will be selected finally. Now we end a while loop. While S prime is not equals to empty set, we select any site little s in S prime and add little s to C. Now we delete all sites from S prime that are at a distance at most 2r from S. Okay, if we break out from the while loop, which means that S prime becomes empty, then we check if the size of C is less than equals to k. If the size of C is less than equals to k, then return C as the selected set of centers. Else, we claim correctly that there is no such a set of k centers with covering radius at most r. Clearly, if this algorithm returns a set of at most k centers, then we have what we wanted. 11.6. Any set of centers C returned by the algorithm has covering radius R of C which is less than or equals to 2R. Next, we argue that if the algorithm fails to return a set of centers, then its conclusion that no set can have covering radius at most R is indeed correct. 11.7. Suppose the algorithm selects more than k centers. Then for any set C star of size at most k, the covering radius is R of C star which is greater than R. Proof. Assume the opposite, that there is a set C star of at most k centers with a covering radius R of C star which is less than or equals to R. Each center little c in capital C selected by the greedy algorithm is one of the original sites in S, and the set C star has covering radius at most R. So there must be a center little c star in capital C star that is at most a distance of R from C. That is, a distance of C star is less than or equals to R. Let us say that such a center C star is close to C. We want to claim that no center C star in the optimal solution, capital C star, can be close to two different centers in the greedy solution C. If we can do this, we are done. Each center little c in capital C has a close optimal center little c star in capital C star, and each of these close optimal centers is distinct. This will imply that the size of C star is greater than or equals to the size of C, and since the size of C is greater than k, this will contradict our assumption that C star contains at most k centers. So we just need to show that no optimal centers C star in capital C can be close to each of two centers little c prime, which is in capital C. The reason for this is pictured in figure 11.5. Each pair of centers C prime in capital C is separated by a distance of more than 2r. So if a C star were within a distance of at most r from each, then this would violate the triangle inequality. Since the distance of a C star plus the distance of C star C prime is greater than or equals to the distance of C prime, which is greater than 2r by triangle inequality. Eliminating the assumption that we know the optimal radius, now we return to the original question. How do we select a good set of k centers without knowing what the optimal covering radius might be? It is worth discussing two different answers to this question. First, there are many cases in the design of approximation algorithms where it is conceptually useful to assume that you know the value achieved by an optimal solution. In such situations, you can often start with an algorithm designed under this assumption and convert it into one that achieves a comparable performance guarantee by simply trying out a range of guesses as to what the optimal value might be over the course of the algorithm. This sequence of guesses gets more and more accurate until an approximate solution is reached. For the center selection problem, this could work as follows. We can start with some very weak initial guesses about the radius of the optimal solution. We know it is greater than 0 and it is at most the maximum distance R max between any two sides. So we could begin by splitting the difference between these two and running the greedy algorithm we developed above with this value of R equals to R max over 2. One of two things will happen according to the design of the algorithm. Either we find a set of k centers with a covering radius at most 2r, or we conclude that there is no solution with a covering radius at most r. In the first case, we can afford to lower our guess on the radius of the optimal solution. In the second case, we need to raise it. This gives us the ability to perform a kind of a binary search on the radius. In general, we will iteratively maintain values r0 less than r1 so that we know the optimal radius is greater than r0. But we have a solution of radius at most to r1. From these values, we can run the above algorithm with the radius r equals to r0 plus r1 over 2. We will either conclude that the optimal solution has radius greater than r0, or obtain a solution with a radius at most 2r, which is equals to r0 plus r1, which is less than 2r1. Either way, we will have sharpened our estimates on one side or the other, just as binary search is supposed to do. We can stop when we have estimates r0 and r1 that are close to each other. At this point, our solution of radius to r1 is close to being a true approximation to the optimal radius, since we know the optimal radius is greater than r0 and hence close to r1. A greedy algorithm that works. For the specific case of the center selection problem, there is a surprising way to get around the assumption of knowing the radius without resorting to the general technique described earlier. It turns out we can run essentially the same greedy algorithm developed earlier without knowing anything about the value of r. The early greedy algorithm, armed with the knowledge of r, repeatedly selects one of the original sites S as the next center, making sure that it is at least 2r away from all previously selected sites. To achieve essentially the same effect without knowing r, we can simply select the sites r as the sites S that is the farthest away from all previous selected centers. If there is any site at least 2r away from all previously chosen centers, then this farthest set S must be one of them. Here is a resulting algorithm. Assume k is less than or equals to the size of S, else define c equals to S. Select any site S and let c equals to the set of singleton S. While the size of C is less than k, select a set s in capital S that maximizes distance of SC. Add site S to C. Now after we break out from the while loop, we return C as the selected set of sites. 11.8. This greedy algorithm returns a set C of k points such that R of C is less than or equals to 2 times R of C star, where C star is an optimal set of k points. Proof that R equals to R of C star denotes the minimum possible radius of a set of k centers. For the proof, we assume that we obtain a set of k centers, C, with R of C which is greater than 2R, and from this we derive a contradiction. So let S be a site that is more than 2R away from every center in C. Consider some intermediate iteration in the execution of the algorithm, where we have thus far selected a set of centers C prime. Suppose we are adding the center C prime in this iteration. We claim that C prime is at least 2R away from all sites in C prime. This follows as the site S is more than 2R away from all sites in the larger set C, and we select the site C that is the furthest site from all previously selected centers. More formally, we have the following chain of inequalities. Dist of little c prime and capital C prime is greater than or equals to dist of S and capital C prime, which is greater than or equals to dist of S capital C, which is greater than 2R. So it follows that our greedy algorithm is a correct implementation of the first k iterations of the while loop of the previous algorithm, which knew the optimal radius r. In each iteration, we are adding a center at a distance more than 2r from all previously selected centers. But the previous algorithm would have S prime which is not empty after selecting k centers, as it would have little s in capital S prime, and so it would go on and select more than k centers and eventually conclude that k centers cannot have covering radius at most r, This contradicts our choice of R, and the contradiction proves that R of C is less than or equal to 2R. Note the surprising fact that our final greedy two-approximation algorithm is a very simple modification of the first greedy algorithm that did not work. Perhaps the most important change is simply that our algorithm always selects sides as centers, i.e. every mall will be built in one of the little towns and not halfway between two of them.